Okay, how in the world does a computer go from seeing just a mess of pixels to actually understanding what it's looking at? Recognizing a cat, or a car, or even your face. Well, today we're going to break down the absolutely incredible technology that teaches machines how to see.
All right, let's just dive right in. When you and I look at a picture, we see stuff, right? We see objects, we get the meaning, but a computer, it sees something totally different. And figuring out that difference, well, that's the secret sauce to all of computer vision.
I mean, look at this. To our brains, a couple of lines and a curve, bam, it's a face. Instantly. We don't even have to think about it, do we? Our brain just automatically pieces it all together. The eyes, the smile, it's just effortless.
But for a computer, that same friendly face is, well, it's just a grid of numbers. Seriously, a 0 could be a white pixel, a 1 could be a black pixel. There's no face in there for the machine. It's just raw, totally meaningless data.
So here's the big question, right? How do we build a bridge from that chaotic jumble of numbers to a clear, simple concept like face? How on earth do we teach a machine to find the pattern hidden in all that noise?
Well, the answer is this really, really clever piece of deep learning that's actually inspired by our own brains, by our visual cortex. It's called a convolutional neural network, or as we'll be calling it, a CNN.
You can kind of think of a CNN as a specialized brain, but just for images. Its whole job is to take a picture, break it down into its most basic little pieces, things like edges and curves, and then figure out how all those little pieces combine to make bigger, more complex stuff. So the whole process for a CNN really boils down to two main jobs. First up is what we call feature extraction. This is where the network literally scans the image to hunt for all the important patterns. And then, second, is classification. This is the part where it takes all those patterns it found and makes a final call. Like, yep, that's a cat.
And it pulls all this off using a really powerful three-step process. Each of these steps is handled by a different layer inside the network. And trust me, each one has a super specific job to do.
Okay, so let's get into the first and honestly the most critical step of this whole thing, the convolution layer. This is where the real magic happens.
So the convolution layer works by using these things that are kind of like digital magnifying glasses. They're called filters or sometimes kernels. And get this, each filter is trained to look for just one specific tiny feature inside that image. Imagine this little filter just sliding across the grid of pixels, one step at a time. And at every single position, it does a little bit of math. It multiplies its own values with the pixel values right underneath it to see how well they match up. The results from that whole scan create a brand new grid, and we call that a feature map. It basically just lights up everywhere that specific feature was found.
But here's the really cool part. The network doesn't just use one of these filters. Oh no, it uses hundreds, sometimes even thousands of them. So you might have one filter that's a pro at finding vertical edges. Another one might be looking for curves. A third one could be hunting for a specific color change. This whole process creates a massive stack of these feature maps, and you can think of each one as a different lens showing a unique view of the original image.
Okay, so after all that, the network has found a ton of features. But now it has a new problem. It's got way too much data. It needs a way to make all that information more manageable, without throwing out the important bits.
Right. So think about it. The convolution layer just expanded the data by creating all those feature maps. The next layer, the pooling layer, has the exact opposite job. Its goal is to shrink everything back down, but to do it smartly. And the most common way to do this is something called max pooling. It's actually pretty simple. It just slides another little window over the feature map and asks one question. In this little area, what's the strongest, most important feature?
And this process has a huge impact. Just by taking the single biggest value from each little section, the network can shrink the feature map down like crazy. In this case, by 75%. But it still gets to keep the most critical information. It just works so hard to find.
All right, so we've found the features, we've simplified them down. Now for the grand finale, putting it all together to actually make a prediction.
So after going through a few rounds of this convolution and pooling, the final high-level features get all flattened out and sent over to what's called a fully connected layer. You can think of this part like a final voting committee. It looks at all the evidence, the combination of features it has, like pointy ears, whiskers, and furry texture, and then it calculates the odds. It figures out the probability that the image is, say, a cat versus a dog. And look, this whole pipeline,
From pixels all the way to a final prediction, it's not just some cool idea on a whiteboard. This is the stuff that's powering technology you probably use every single day, without even thinking about it.
I mean, think about it. When Google Photos finds all the pictures of your dog, that's a CNN. When Amazon recommends a product, that's a CNN. That automatic photo tagging on Instagram and Facebook? Yep, CNNs. And it goes way beyond that, to self-driving cars and even analyzing medical scans in hospitals. CNNs are really the engine running behind the scenes of all modern computer vision.
So by building a system that basically learns to see the way we do, starting with simple little lines and building up to big, complex ideas, we've given machines a real sense of sight. It's already changed our world in so many ways, and it leaves us with a pretty mind-blowing question to think about. Now that machines can see, what are they going to understand next?